All right, so in this example, we have -3 secant, quantity of 4 times the quantity of theta minus 5 pi over 7, close, minus 9, and we are going to graph this trig function, and then we're going to go over how to find the domain and the range properly. We want to use the likes of interval notation to do that. We don't want to try to do this using an inequality. It'll be a complete nightmare. So it's kind of going to look like interval notation, more so for the range. The domain is going to be written sort of as a solution set builder notation, and that's where we're going to use like a curly bracket and sort of an equation or explanation explaining the domain in a special way. Anyhow, we're graphing secant. When we're graphing secant, you have to remember that secant is a reciprocal of one of the 3 basic functions, and it is the reciprocal of cosine. So what I'll do on the paper first to make my life a little easier is I'm going to draw dotted a negative cosine graph, and then I'm going to draw secant off of that, and then I'm going to make the tick marks and axes after the fact. Drawing the actual graph on the paper should be like one of the easier parts. You should be able to identify what it looks like. So what do we mean by that? If you have a positive cosine graph, positive cosine of theta, obviously we don't always write the plus sign. Well, we have 0 and then the tick marks going all the way around to 2 pi, and cosine is all the output values, or the x values there. We're going to plot all the outputs. What is cosine at 0? It's 1. What's cosine at, this is pi over 2. What's cosine at pi over 2? It's 0. Cosine at pi is -1. Cosine at 3 pi over 2 is 0. And cosine at 2 pi, when we're dealing with the parent function, it should make sense. It should be the same as cosine of 0. They're coterminal angles. So cosine, just watch your little concavities. These are concave down, looks like a frown. This is concave up, looks like a cup. So that right there is one cycle, one full cycle of cosine. And if you keep drawing it in both directions, if you look at a different piece of it, like if I moved over and I was like, let's look at it starting from here. If I consider this cosine function, this is like a challenging question, like kind of show what you're thinking. If I look at cosine as if it were started from here, how could I write this equation not using cosine? Does anybody know how I could write, if I kept my cosine graph going and consider it from this spot, if I look at it from here, how can I write the...
It's a sine equation with a shift?
Yes, it's going to be a sine equation with a shift. Now, based on these tick marks you could kind of figure out. So I'll ask about this later, but kind of think about this if you can. At the same time, if you think you're pretty good at this, if you could think about 2 things at once, think about what that shift is. And I want you to also think about why that works. It's something we learned as far back as lesson 6, and this is more like lesson 17. So think about it, consider it. I'll ask you about it later. All right. Now this again, I'm just going to highlight the positive cosine because I did draw extra of the graph and it gets to get a little cluttered, so I don't want this to be too crowded. That's positive cosine. I have a negative out front, so dotted, I'm going to draw negative cosine. And you should start memorizing what these look like, but it's just going to have a vertical reflection, so it'll look shape-wise like this, concave up, concave down here, and then concave up again. And again, it continues forever and ever. All right, great. So let's go ahead and draw that. So I'm going to draw some dots on my paper. These are a little far apart. I feel like I'm going to regret this decision. Let me squish them a little lower, because if you remember, since we're graphing either secant or cosecant, that it kind of goes off in the other direction. So I kind of need to consider that and leave some more space. Now I want the horizontal space between my points to be pretty consistent. And I'm going to draw my negative cosine graph dotted. So this part is concave down. I like to do the middle part first because like I mentioned, you guys draw some weird things sometimes and these look really pointy. So if you look at your notebook, like maybe yours is pretty pointy, so just be careful of that. Then this scoops the other way and this scoops the other way. All right, there's the shape. So what part did I address so far? I already addressed the negative, and I already addressed, well, part of the fact that it's secant. Now, secant. Let's wait to draw that. Let's draw in -9. -9 is the sinusoidal axis. That's the middle of the graph, so that's actually pretty easy to do. Now, I'm not drawing my x or y axes yet because I'm trying to be efficient here, and I'm going to write down that this is my y equals -9, and I'll make a little note if you want to call it the midline, you want to call it sinusoidal axis, call it whatever you'd like, sinusoidal axis at y equals -9. That means, like, if I'm going this way, up, my x-axis will be up here somewhere, or my theta axis, whatever I call it. 3. Well, I can involve the 3 a little bit. If this is -9 and 3 is out front, this distance is 3, this distance is 3, and 3. So I could think that this over here is going to be then -12, and I could think that over here, that distance, y value will be -6. Again, I don't know where my y-axis is going to go yet. Actually, maybe I do. This is not so bad. Minus, I move to the right. So my y-axis will be on this side because everything will be positive. So I can go ahead and label some of this information. We said that was -9. This is -12. And that was -6. And if you remember from previous discussions, sometimes this is moved to the left. And I don't know if all of these will happen to the left of the y-axis or if I'll cross over from negative tick marks to positive. So I like to wait with my y-axis whenever possible. Now, I can just do a little zigzag right here because I don't have time to like dilly-dally with this and do every single thing to scale. And now I'm going to go across and draw my x-axis. Above each of these, I'm going to put my tick mark. This way I know it fits in my notebook and I don't have to worry about running out of room. So what have I taken care of? I've taken care of the -9. I've taken care of the 3. And now we're going to look at the fact that it's secant. It's not cosine, it's secant. So these two spots are considered the zeros. Think of them as the zeros. If they're slicing the sinusoidal axis, they would be equal to 0 for cosine, right? 0 and 0. All these other transformations are just coming along for the ride, so don't overthink it. If this is secant, it's the reciprocal. What's the reciprocal of 0? There's undefined. So everywhere that your cosine was 0, your secant will be undefined. So that is where you're going to put the vertical asymptotes. Those indicate the places where our graph will be undefined. From that, now another awkward part is actually drawing in these pictures. Again, think of it as it relates not so much to the transformed one, but to more or less the original. Normally, these are like up 1 unit and down 1 unit, right? The reciprocal of 1 is what? The reciprocal of 1 is
1.
Still 1, right? So that point stays. And the reciprocal of -1 is -1. And the reciprocal of -1 is -1. Those are the same. So secant and cosine have those values in common. Next. Again, I'm just, for the logic of it, pretending that I'm dealing with the parent function. I'm not worrying about like these actual stretched out numbers. The behavior just is all adjusted together. But if we pretend we're looking at, say, a tick mark over here where it's a half a unit up, if you remember, right? Because like some of the values for cosine you'll hit are what? 1/2, root 3 over 2, root 2 over 2. Root 2 over 2 is about 0.7 something. Root 3 over 2 is about 0.9. So like here's 0. Maybe this is a half. Maybe this is 0.7, 0.9, 1. And then it comes down. So that's what those are. But 1/2 is probably the easiest one. If cosine equals a half, then what would secant equal in that same scenario?
2.
It would equal 2. And if that's 1, where's 2? Well, up higher, right? Somewhere over there. Again, if cosine is a half, halfway up, well then secant is double the maximum units up, whatever it might be. So here, as, again, even thinking of it, I'm just going to point, say, I'm looking at this hump here, right? If that's 0 units up and that's 1 unit up, let's pretend right here I'm at 0.1, 0.2, 0.3, or let's even do like, here's 1/2. Let's say I go a little closer, 1/3. If that's 1/2 up, say I'm 1/3 of the way up. What's the reciprocal of 1/3? Here I'm halfway up, I'm at halfway mark. A little lower, I'm only 1/3 of the way up. What's the reciprocal of 1/3?
3.
3. So instead of being 2 up, you'd be 3 up. What about 1/4 of the way up? If cosine's only 1/4 of the way up, what's the reciprocal of 1/4?
4.
4, even higher. I can't even fit it, right? If it's only 1/100th of the way up, the reciprocal of 1/100th is 100. If it's even closer to 0. And this concept, if you're taking calc next year, very important. It has to do with limits, so let this marinate your brain a bit. But if you're 1/1,000,000th unit above the axis here, the sinusoidal axis, the reciprocal would be 1,000,000, way up there. So that's why as we get closer and closer to the asymptote, where this one would get smaller and smaller, its reciprocal is going to get bigger and bigger and bigger and bigger forever. And the same on this side. So think of it as a reciprocal refliprical. So like this little frowny face, turn that frown upside down. Refliprical, it flips over and now it's a happy face. Okay? Reciprocal, refliprical. I have a funny feeling if I looked at your notebooks, at least one person drew this little squiggle in a crazy way. I could almost guarantee it. Anyone want to admit that that squiggle on their notebook is definitely not doing that? Anyone? No one's admitting? Yeah? It's wonky on yours?
Yeah.
Okay. And I'm telling you, these 2 squiggles are the ones that are very, very wonky for people. Something that helps you see it better is if you continue the dotted line like this a little bit, it'll help you see that other little U shape over here. And then it helps you see that, this would be another U going down, another U going down, so on and so forth. But we didn't need everything. So what did I just take care of? I just drew actual secant from cosine. Again, it's a little awkward. Drawing in cosecant from sine is a little easier because your asymptotes are at the ends and in the middle. So you see like a full U shape and another full U shape. Secant's awkward because the asymptotes are kind of in the middle. It's just weird. So we took care of this. 2 more things to take care of. One that's pretty easy is the minus 5 pi over 7 because it went to the right. So this tick mark, the very first one, is just 5 pi over 7. Winner, winner, chicken dinner. We're done with that. Last thing to take care of is the 4. 4 is the b value. It's bigger. Now, sorry, it's blurry. This is a scenario where you can finally really see why these numbers are 4 when it's going to compress it to 1/4. So humor me for a second. The 4 goes in for the period, and the period is 2 pi over 4, which reduces to pi over 2. We'll see what we need to do with that. That means 1/4 of that is 1/4 of that, which would be pi over 8. It's 1/4 of that right there. And I need to keep adding pi over 8 to my starting point. I need a common denominator, which will be 56. That's annoying, sorry. 5 pi over 7, multiply top and bottom by 8, and I get, what, 40 pi over 56? Correct me if I make a random mistake, because that would be awkward. And this, top and bottom by 7, and we get, what, 7 pi over 56? Add that each time. So 40. Again, this is why I like to leave common denominator. Just leave it across. Don't worry about reducing. Plus 7. The next tick mark here is 47 pi, a little squash, sorry, over 56. The next one right here will be add another 7 to 47. So we get what? 54 pi over 56. Right over here, again, correct me if I screw up, 61 pi over 56. And last would be 68 pi over 56. Don't even reduce it. it is not worth your time or the stress or a careless error. Just leave them like that so you know how far apart they are. You could check things and work it all out. So that is your graph. We took care of the 4. Now this 4 again. If I didn't have a stretch or compression, here is one normal, I'm just going to look at cosine for a minute. One normal cosine wave, which normally would fit between 0 and 2 pi. But what if I told you 1, 2, 3, 4? What if I told you this is 0 and this is 2 pi? Was the cosine wave, okay, this is 2 pi and this is 0. Was the original cosine wave compressed horizontally or stretched horizontally? If I could see all of this, all these cosine waves, did I have a horizontal stretch or compression if I am going from 0 to 2 pi and seeing this much cosine happening?
A compression.
Right, a compression. The compression means what number goes in the equation for cosine? Y equals cosine blank x. How many full cosines do you see? Think of it as like a tile in your new kitchen. You love trig so much, you're tiling your kitchen using trig. How many full cosines fit right here?
4.
We fit 4 in the typical space. That 4 is your frequency. So that's how many you fit. And if you're going to fit 4 in the same amount of space, you have to compress it. So that's why it seems a little bonkers when you're filling in a 4 but making it smaller. So the trig, being able to see that many cycles in a certain window, helps you understand that. Hopefully that connected a few dots for you. But that is the end of graphing this. So I'm going to end this video, and in the next video I'm going to go over domain and range, but I want to give you guys a chance to share if you think you know what the answer would be before I start recording. So anyone who understands this watching it, that's fine. Address it with a thumbs up. But if you don't, please put a thumbs down by all means so I know to do more videos of this type of example.